Hello. Here we will derive what is known as Fermat's little theorem. We start by preparing for it the assumption that P is a prime, and the preparation result is going to be a compact, simple formula for computing the pth power of the sum. If we are interested in congruences mod P, the answer is going to be extremely easy. It's just going to be the sum of pth powers. So that is sometimes known as a freshman's dream. Instead of a complexity of Newton's binomial formula, you just have this. So that is what we prove first, and it follows from binomial formula. According to this, we have the sum of monomials coming with binomial coefficients. The sum goes through p plus 1 terms. Binomial coefficients can be compactly written as the ratio of factorials, p factorial upstairs, I factorial downstairs, p minus I factorial downstairs as well. So what happens when p is a prime? These factorials terminate at something which is less than p, so any of those factors will be less than p. And that means that will not be divisible by p, so p upstairs, which is a part of the factorial upstairs, will not be cancelled. So this, if I is not p or p minus I is not p, so if I is not 0 or p, this will be divisible by p. So here is this key result, that this for I not 0 or p, this is divisible by p, hence congruent to 0 mod p. And that is the compact answer for the whole sum. So everything which is in the bulk of the sum, everything which is not the extreme terms, these two extreme terms, will disappear. So we have it. End of proof. Now we are ready to prove Fermat's theorem. What it says is that anything to the pth power is congruent to itself mod p. So any integer. We can think of x as a natural number and prove this by induction. Induction on x, of course. The base of this induction will be 0 weight of x. So when x is 0, the pth power of 0 is 0, of course congruent to itself, mod p. And the step, so that is the base, and the step will consist of moving to a plus 1, checking it for a plus 1 if we know it for a. But by this previous result, that can be written as a to the pth power plus 1 to the pth power, which by assumption now is congruent to a, and this of course is congruent to 1. And so we are done. The induction step is done, and we have a Fermat's theorem proved. Let me just finish by reformulating it slightly. We can make it less general, assuming that x is a special congruence class mod p, such that it is not 0 mod p. So for any such, we know that it is such x is invertible, so we can cancel it out from the congruence, and we'll have a different congruence that p minus first power of x is 1 mod p. So this also is known as Fermat's little theorem, and that will be useful later. See you then. Bye.